concept 2, exponential decay. So this equation is very similar to our exponential growth equation. The only difference is this subtraction instead of addition. So instead of adding our rate of growth to 1, we are subtracting it from 1, which means that our rate of growth overall is going to be less than 1, which is going to have an effect of decreasing our original amount rather than increasing it. Okay, and again, a has to be greater than 0 for this. Excuse me, for this to be a true exponential decay equation. If we start with a negative original amount, it'll be a different type of problem. Okay, so this might be a little on the nose, but I think it is a good example of a question where exponential decay fits. So if we have 1,000 people in quarantine that have the coronavirus, and each day 5% of them recover, how many people will still have the virus after 20 days? Okay, so we are really just still plugging in values. Okay, I've got 1,000 people. 1 minus 5% as a decimal, 0.05. All right, and then we take that to the time period. We're going for 20 days in this case. All right, doesn't really matter if the time period is days, years, 2-month periods, whatever, as long as you're making sure that you know what the time period is and that those match up. Okay, so I've got 1,000 times 0.95 to the 20th. Take our calculator. 0.95 raised to the 20th gets me 0.9025. Multiply it by 1,000, and we get 902 people are still infected, and one person's halfway there. Okay, and that's my answer. After 20 days, we've still got a number of people infected, but this is but 97.5 have recovered. All right. Okay. With decay, we have the most common type of problem we get with decay is going to be half-life. And half-life, I think everybody's heard of it, but basically half-life is just the time it takes for some substance to decay, for half of that substance to decay into another substance. All right. So our formula is actually much simpler because our R, our rate of decay, is always going to be 0.5. So we're always taking half of our substance away. But what really changes is the T. So it's no longer just the number of time periods. Okay, now it's the number of half-lives in a given time period. So that does add a additional calculation you got to figure out sometimes to be able to solve these problems. Okay, so if we have carbon-14, which is what we use for carbon dating, it has a half-life of 5,730 years. And if we're looking at a 1,000-gram sample of bone from an archaeological dig that is said to be 28,000 years old, how much carbon-14 would we assume that we would find? All right, so how much would be left out of that 1,000 grams if we were to date this and it was 28,000 years old? Okay, so our first job is to figure out, well, how many half-lives we have in that time period. Okay, so if we have 5,730 and 28,000. Okay, let's see what we get. 28,000 5,000 divided by 5,730. We'll probably round that to, let's go ahead and round that to 5. We'll keep things fairly simple. We'll round that to 5. So we'll say that's about 5 half-lives of carbon-14. Okay? So if we've got 5 half-lives of carbon-14, we're going to start with our original amount, 1,000 grams, multiplied by our 0.5, our half-life, over 5 half-lives of that material. Okay? So 0.5 raised to the 5th times 1,000. And it looks like out of that original 1,000, we would have 31, or we would expect somewhere about 31.25 grams of carbon-14 to remain. Okay? And that's how half-life and exponential decay works.